All right, let's get started. So, first of all, any questions for homework, for everything else? Yeah, all the videos should be uploaded. So if you miss anything, just take a look. All right, so yeah, in our last lecture, we finished talking about the four most important inequalities, right? And then we start talking about the information source and the asymptotic equipartition property, right? So yeah, for the data processing inequality, so it basically tells you that if x, y, and z form a Markov chain, right? And then if you compute mutual information between x, y, or y, z, it has to be less than or equal to the mutual information between x and y, right? So basically, so the key is that, so if you compute the mutual information between something that is farther away, so that will be less than the mutual information between two variables that is more close. Okay, so yeah, that's basically the idea. And that's why it's called data processing, right? So basically, if you consider z is a processing version of y, and then you can see that between x and z, the mutual information between x and z, it has to be less than or equal to the mutual information between x and y, right? Processing the data will kind of reduce the mutual information. All right, so yeah, this is what I just said, right? So if this is a processed version of y, and you can see that mutual information between x and gy will be less than the mutual information between x and y, okay? Yeah, and as a byproduct, so we can also prove this inequality, right? So basically the approach is exactly the same, right? So here, so given z, you can see that the mutual information between x and y would be less than the mutual information between x and y, okay? This is kind of a new inequality we have not seen before, right? So what we did see before is that if given x, and then the mutual information between y and z is less than the mutual information between x and y. Okay, so sorry, between y and z, right, in that case. Okay, so yeah, but we haven't seen that before, right? But the proof idea is exactly the same, right? So basically, if we have Markov chain, then in general, condition on mutual information will reduce the mutual information. Okay. All right, so, and that is the data processing inequality. And then we talk about the funnels inequality, right? So one important outcome for the funnel inequality is that, so we could have a lower bound for the error, right? So without knowing almost anything. Okay, so this is a very, very powerful theorem to have a lower bound for the error. Okay, so yeah, and later on, so probably if we have time, so we can see an example today, or definitely next time, how we are going to use funnels inequality to prove the converse result, which is the impossibility of something. Okay, you'll see how we can use that. All right, and then we introduce you the concept of the information source, right? So here, in this class, so in most part, right, not in all the part, so in most part, we care about this so-called IID sequence, okay, or IID, or memoryless information source, okay? It basically means that we have a sequence of random variables, right? So it is countable, right? It could be, infinite numbers, right? But the important thing is that the probability distribution of each of them is identical, and then they are independent, okay? So that is very, very important. So it seems a very kind of we have a very heavy assumption on this, right? But later on, you're going to see that this is very powerful. So we can use a lot of results from this assumption, okay? And then we introduce you what is a weak law of large numbers, right? So basically, it means that if we have a number of these random variables, right, and then their IID. So if we estimate their average using this formula, right, we just compute the average of them, right, and then we can show that, so this average will approach to the expectation improbability, right? By improbability, we basically mean that when it goes to infinity, so this probability will become 0. Okay, so it basically means that with probability 1, so the difference between this and that will be less than epsilon, right? So it means that it will in a very small neighborhood of the expectation. Okay, so this is the weak law of large numbers, right? Why it is weak? It's because the convergence is in probability. Okay, so if it's convergence in something else, we can have the strong law of large numbers, right? But the idea will be the same. Okay, so yeah, we just need this in our class. Right. Okay, so yeah, this is, and then we briefly talk about what is AEP, asymptotic equipartition property, right? So basically the idea of this is that it turns out that for this kind of source, right, so, and we can see the probability of almost any sequence will appear either with a probability, same probability, or with almost zero probability, okay? So that's kind of very interesting. So let's continue talking about that. And okay, so today is our lecture number 12. So today, number 1, we're going to continue talking about AEP, okay? And then we're going to talk about the data compression. Okay, and or in Shannon word, it's called source coding. Okay, and so the AEP is in our chapter 3, and this is in our chapter 5. Okay, so we're not going to have any homework on chapter 3, I guess, but we're going to have our second homework on chapter 5. All right. Okay, so let's recall our last example. Okay, so we consider a information source x1, x2, up to xn, and so on. So we assume that is IID with the probability px. Okay, and for simplicity, we consider this is a binary source, right? So basically, it means that each random variable follows a Bernoulli distribution. Okay. So basically, we assume that p any x I equals to 0, we denote that as p0 equals to 1 minus p. And the probability that xi equals to 1 equals to p1, so that equals to p, okay? So it's a Bernoulli distribution, all right? And then we could compute the probability distribution of the sequence, right? We assume we have a sequence of random variable that has n random variables, right? Then what's the probability of that? Yeah, that's how, we're going to compute that, right? But the first step is that we know they're IID, right? So we can basically break them into this, right? From 1 to n, right? So that's basically, because they're independent, then we can, break them, right? All right, so this is the definition of independence, okay? At least for the discrete random variable. All right, and then as what Mark said, right? So now we can, make it more explicit in terms of p and 1 minus p, right? So p is a probability that there's a 1, right? And how many ones? So we can just write a summation of all of them, right? So this is the number of ones, right? Because if they're 0, then it does not contribute to this, right? Right? And then the number of 0 is 1, the probability that 0 happen is 1 minus p, and then to the power of n minus this guy. Right, because there are total n random variables, right? And if this are number of ones, and then n minus 1 is this number of zeros. Okay, so that equals to that. So any questions? Okay, great. And then, so let's see, what does this guy equal to, roughly speaking? Okay, and so basically, we briefly talk about that by the law of large numbers, for example, right? So when n is large, right? So this is basically the summation of the random variable, right? So we know the average of it will approach to P, right, which is the expectation, right? So can you tell me now what is the number of ones? Okay, so that will be roughly equals to
n over 2, or the number of possible outcomes?
yes, n over n times p, right? If p is half, then it's n over 2, right? Very good. And similarly, number of 0 will be roughly equals to n times 1 minus p, right? Yeah, roughly speaking, okay, yeah. Okay, and with that, so we can compute the approximate probability of this guy, right? So that, roughly speaking, that will be equals to p power of this guy, right? And this guy equals to np, right? And then 1 minus p equals to n minus times 1 minus p, right? And then the probability roughly equals to that, right? So now let's make some changes here, right? So now how about I write this as this form, okay? I use 2 to the power of log 2, this guy, right? So that they're equal, okay? And then now I can break the exponent right here. So basically, yeah, this equals to 2 power of. So I have an np here, and we have a n times 1 minus p here. So they can be brought into the front, right? So basically what I got here is nothing but we have a n p log p plus 1 minus p log 1 minus p, right? So we break this first and then take the exponent out, right? So then we get that, okay? So next, let's see, what is this? So does that look anything familiar? Yeah, what's that? Say it louder.
Binary entropy.
Yeah, binary entropy function, right? Not exactly, almost, right? So we have a minus sign in front, right? So this is basically minus, yes, minus this, right? Therefore, then we get this equals to, is 2 minus n h2p, right? We kind of have seen that before in our last class, but here is another kind of very rough derivation of it, right? So it's not a formal proof, it just, kind of intuitive proof, right? So this is the binary entropy function. Okay. All right, very good. And then let's see, what does that tell you? So it basically tells you that, okay, so this guy will roughly equal to this guy. Okay? So it basically means that, so almost everything will equal to this. So that's why it's called equipartition property, right? Asymptotic basically means that when n has to be large. Okay? So it basically means, then it means that with very high probability, if you randomly sample a sequence there, okay, and then roughly speaking, you're going to get NP ones and NP zeros. If you don't get this number of ones and this number of zeros, probably that will not happen. Does that make sense? Okay. Yeah, this is kind of this concentration result. Okay, so it's pretty interesting. Okay. Yeah, I think that'll be it. All right. So yeah, this basically introduced us the concept of this typical set and a typical sequence. Okay, and for a sequence, that satisfies this property, so we call that a typical sequence. Okay, and the set of the typical sequence is called a typical set, right? Because most likely they will happen, and for everything else, they may not happen. So that will happen with probability almost 0. Okay, And before introduce you this concept, we need to talk a little bit. We need to talk a little bit on kind of another definition of the typical set and typical sequence. So those are used less often, right? So we're going to use this concept, in our class. But there's another one. So I want to introduce another one first. And if you want to read further about information theory, right, and you'll see that this definition also used quite a bit, right, but in a more advanced setting. Okay. So let me introduce you this concept, which is kind of more intuitive than this even, right? Because we need some derivation for this, right? So why the probability equals to related to the entropy, right? We need some derivation on that, right? But for this definition, so it's kind of very natural. It's the most natural definition of the typical sequence. Okay, and let's see what we're going to do here. So we define a vector of x here. So that is from x1, x2 till xn, right? And that is in this superset. Okay, and we assume the empirical PMF of x as follows. Okay, the empirical PMF of x is defined as, so we use this notation. So if we have two textbooks, right? So one is the Cohen and Thomas, right? So that's a required textbook, and then we have another one called Network Information Theory, right? That's not required, but if you look at that book, then you can see this definition there. Okay, so the empirical definition basically means this, right? So it's a very natural definition of the PMF. So basically, now we have a vector, right? So if we sample the vector, so what we're going to do, to approximate the PMF is as follows, right? So basically, we're going to count the number of I where xi equals to small x, and then we divide it by n, right? So this notation means cardinality, right? So we want to compute. So this is, roughly speaking, so this is the probability of x, right? Giving you the vector x, right? How can you compute it? You count. So what is the number of xi equals to x, right? And then you normalize it by the total number of random variables. Then you get. So this is not exactly PMF, but it's a good estimate of the PMF, right? When n becomes large, then this estimate is pretty good, right? Okay, yeah. Okay, yeah, this is very natural for all x in this x. Okay, and so this is also called referred to as the type of x. Okay, we call that type. All right, so now let's take a look at one theorem. So this theorem is kind of obvious, right? So basically, we want to say that when n becomes large by the law of large numbers, so this will approach to the px, right? Okay. So now we assume that this random variable, this random vector, denote an IID random vector with everything follows this distribution, okay? And then by the weak law of large numbers, then we can get that as n approaches to infinity, and then so this will approach to, we should write equal here, px for all x. Okay, so this equal basically means convergence in probability. Okay, similar to the law of large numbers. All right, and given that, we can define a typical set from this definition. Okay. Yeah. Yeah, for a given PMF, Px on x, and epsilon bigger than 0. So this epsilon can be arbitrarily small number. Okay, and then we call the epsilon typical set of sequence x is defined as, so we use this notation, it's a calligraphic T, epsilon, n. So yeah, this epsilon basically means this epsilon, this n means the length of the sequence, okay? So that equals to all x in here, and then so the value of this guy and the value of the PMF, so they are not very different, right? So this is less than epsilon times px for all x in x, okay? So basically this gives you all the sequence such that, so this guy and this guy are pretty similar, right? Not equal, but the difference is only this. So it can be arbitrarily small, depends on epsilon, right? If you give a big epsilon, this set can be very large, right? But if you give a small epsilon, so this set could be very small. Does that make sense?
What was like the epsilon referring to again?
Say again?
What was like the epsilon like referring to again? Like
It's just a small number. It's an arbitrarily small number. You can think of that, right? So for example, let's say if epsilon is 1, right? Then as long as it's less than 2 times the probability of px and bigger than 0, then we're good, right? But if epsilon is like very close to 0, like 10 to the power of minus 9, then it has to be very close to the px, right? Does that make sense? Yes.
So is that epsilon typical set basically you define like the range of epsilon?
It's a good question. Normally, in practice, we consider epsilon as a very small number, but not 0, right? Because if epsilon is 0, then this and that has to be equal. Then it's not interesting, right? So yeah, normally we consider epsilon as a very small number, right? We can imagine this is it's very close to 0, but it's not 0, right? So later on, you're going to see, probably today or next class, you'll see that. So in information theory, so we always need to deal with this kind of epsilon here, right? For example, when we talk about what is the error of decoding, or what is the error of something, what is the error of x and x hat are not equal, right? Normally, we do not consider when this error is exactly 0. It has to be close to 0. Okay, something like that, right? You can see that if epsilon is 0, then this and that has to be equal, right? Then the number of such a sequence may be small, right? So it's not very interesting, right? So yeah, normally we consider a small but non-zero epsilon. Doesn't make any sense? Yeah, you'll see. So that will make sense probably very soon. Okay. All right. Yeah. So this is the typical set. The reason I want to introduce you that is it's kind of the origin of information theory. So yeah, this is the most natural way to define a typical set, right? It's just a direct application of law of large numbers. Okay. And if there are many books that use the word type here, right? Type basically refer, this thing, right? So, if you read other books and you see the word of type, then you see what they mean by that exactly, okay? So yeah, but in our class, so we're going to use another definition for the typical sequence, so which is what we just seen before. We use entropy to define that, okay? So we call that, and also this was used in our book. So this is called entropy typical set. Okay, so this is in Cover and Thomas' book. Okay, so let's see what's the definition of it. So now, again, we let this be an IID random vector. Okay. Or in this case, we can think that is a memoryless source, right? Okay, and then we can see that the probability of this equals to this, and this is what we have seen before, right? And from here, we can define or compute the self-information of this, right? Hopefully, you still remember how to compute self-information, right? So that is nothing but log 1 over px, right? And then by using this, so we can replace this by that, right? And then, so basically what we can get is a summation of this, the self-information for each of them. Okay, and this equals to nothing but log 1 over pxi. Okay, so this is basically that, and then we can define our typical set using the self-information, right? So basically, from here, we can write a similar theorem, right? So remember, so this is how we define the type, right? And then we can get this theorem, right? So similarly, so now we can get a similar theorem for what? For the self-information, okay? Okay, so now for any, so now we use a epsilon prime, right, to distinguish it from the previous definition, right, where we use epsilon, right? So for epsilon prime, and then we say the limit of this minus the entropy bigger than epsilon prime. So that is basically 0, right? So again, so this is the application of the law of large numbers. Okay, and from here we can directly define the typical set, or the entropy typical set. Okay, so for any epsilon bigger than 0, so we define. So now we use a calligraphic A to define this set. So A basically means what? Yeah, I don't know. Yeah, we just use A here. So this is for all the x, the vector x, and then so we have this. Okay, yeah, the self-information between this and then n times the entropy, right? It's similar to this, right? We'll just multiply n here, okay? So it's less than or equal to n times epsilon prime, okay? We define that as the set of epsilon prime typical sequence, or epsilon prime typical set. Okay, so this is the basic definition, right? So you can see it's very similar to what we got here before, but here we just use the empirical distribution, but here we use the self-entropy. Okay, and this is what we have seen before, right? And from here, from this formula, so we can see that, with high probability, so basically we can get, so this guy would be less than or equal to what? So this plus that, right? So n times hx plus epsilon prime, right? And then on the other hand, so this guy will be bigger than or equal to what? N times hx minus epsilon prime, right? Yeah, any questions so far? Right, and from here we can see that, remember, so we, as we said before, right? So this guy basically equal to this, right? So basically, so this guy equal to log 1 over px, right? And from here, so we can see that, right? So let's assume it's log base 2 here, right? And then we can manipulate a little bit, right? So we basically we take an expectation on 2 on both sides, right? And then switch them, so we can get the upper bound and the lower bound for px, right? If you do that, you can see this is less than or equal to 2 minus n hx minus epsilon prime, and bigger than or equal to 2 minus n hx plus epsilon prime. Okay, just do some manipulation. Okay, and this only works for x is in the typical set. Okay, so basically from here you can see that it's almost the same as what we said before, right? So from here we could roughly conclude that, so this guy, roughly speaking, it equals to this guy, right? When epsilon prime is very, very small. Okay, so this is basic. From this definition, we can see exactly what we want before. Okay, any questions? Right, so from here, you can see there's a very important conclusion. So all typical sequences have roughly the same probability, or so that's basically, it's called AEP. Okay, and you can see that there will be a lot of advantage if we analyze only the sequence on AEP. So sorry, on the typical set. Okay, any question? All good. Okay, so now we have two definitions of typical set, right? So one is this entropy typical set, right? So at the first glance, it may not be extremely intuitive, but after some analysis, it is pretty intuitive, right? And the other one is a typical set we define directly on the empirical PMF, right? So now the question is that, are they the same definition? In other words, so what are the relationship between these two definitions, between the two typical set, right? So we know one typical set is this guy, and the other one is A, right? Of course, so they have two different epsilon, but we can define, epsilon is on what we define, okay? So now the question is that, are they the same? Or if they're not the same, then do they have any relationship, right? It's like one including another one, or they are disjoint, or they are like overlapped. So which one is the case? Right? Intuitively, what do you think?
Maybe overlap.
Maybe overlap. You mean they're the same, or? Yeah, overlap basically means that there could be, some element could be in only one of those, or one could include the other one. right? Which one do you think? Okay, so next we're going to answer this question. Right? Think about that while I'm writing. So what is the relationship between typical set and entropy typical set? Yeah, take a guess. What do you think?
Probably say one's like a subgroup of the other.
Yeah, which one's bigger?
Let's say like the left one, like the typical set we defined first.
You think this one's bigger?
I'll say yes.
Mm-hmm. Any other answers?
Yeah. I feel like maybe it's the other one, like that. The A one is bigger.
You think A is bigger? Why is that?
Like I'm thinking like intuitively to be in T or something, or T, you need to have similar structure and like the probabilities of each thing, but with the other one, it's more just about like similar uncertainty. So that seems like easier to match.
Very good, very good. Yeah, you're right. So basically, so the A is bigger, right? I think your intuition is very nice. So basically, what Mark said is that, so for the type here, so this guy is defined for each, the probability of each x, right? But here, it's defined, it's not on the probability of each x. It's a function of it, okay? It's an average thing, right? So basically, I don't know whether it makes sense to you or not, but intuitively, it's somehow, if x is here, I think it's pretty, what's the sound? Yeah, I think it's relatively obvious to show that that x will be here, right? Think, so if the empirical is very close to probability of each x, right? Then it will probably, if we compute the function on this probability, it will be probably very close to the entropy, right? But here, vice versa may not be true because it's an average thing. It's a function of some of the p, and then it's the average of it. So it seems a loser, right? So if you want to say the average satisfying something, it doesn't mean each of them will satisfy something, right? And this guy is defined on each of them, sort of like that. Does that make sense? I think this kind of intuition, yeah, but we're going to show that, okay? But it's a very good thinking. So theorem. Why there's always a sound here? What's that? Who knows what that is? So, see that before? Yes, very annoying. Yeah, farther. Okay, yeah, let's write it down. So basically, but that's intuition, right? We need to make it precise. So first of all, we need to see the relation between epsilon prime and the epsilon, right? So it will not hold for any epsilon and epsilon prime. Okay, let's say if we let epsilon prime and equals to epsilon times hx. Okay, so this is a specific epsilon prime, and then, so we say this guy is smaller, so that is inside of this guy. Okay. All right. Okay, so this is not in our book, right? But why I want to show you this theorem? So one of the reasons is that I want to show you a very, very important lemma that we're going to use all the time. Okay, and this is a good example to use this lemma. Okay, so this is called typical average lemma. Okay, so this lemma is as follows: let x is in this set, and so we use g to denote a function. So g denote a non-negative function. On x, okay? And then we have the following inequality. So if we compute the average of g xi, okay, and then we can upper bound and lower bound this, right? And the upper bound is this guy, expectation of gx, and the lower bound is 1 minus epsilon expectation of gx. Okay, so this is average typical lemma. Where am I? Okay, yeah, this is basically a very important lemma. So let's prove this lemma, right? So basically, this lemma tells you that if x is in the typical set, and then if we do a summation of those, okay, and then this has to be between these two values, okay. So it's very strong lemma. So let's prove that. Let's see. How can we prove it? So basically, now let's compute this. Okay. Right. Remember now the important condition here is that x is in the typical set. Right. So then, before that, we need to write that in terms of the PMF. I mean the empirical PFM. Right. So this will equal to what? Right. We're going to group it. Okay. So with the same number of ones, then we're going to group them together. Right? So basically, this portion, so give you the portion that we have an x, right? So this times this guy will basically give you the portion that x appear this number of times. Of course, this multiply n would be the number of times, right? And then we sum over all the x here that is in the x. Right? So does this make sense to you? Right? So this is a portion of x appeared, right? And then we times that, so that will be equal to this, right? Because we have 1 over n in front, right? If there's no 1 over n, then we just multiply n here, okay? And then, this is very important step, right? After that, our life is easy, right? Because by using the definition of the typical set, we know that can be upper bounded by 1 plus epsilon times the probability, right? And then we're done. Okay, so this would be, and then use the definition. Right here is a definition of this, and then we can get this is 1 plus epsilon, and then now we have this. Okay. Right, and so basically that equals to 1 plus epsilon expectation of gx. Right? So, okay. So basically that'll be it, right? So And so this is the one side of the inequality, and similarly, we can show that this guy will be bigger than or equal to 1 minus epsilon expectation of this. Okay, and then we're done. All right, so any questions? Okay, yeah, if no question, so now we're ready to prove the theorem. Okay, so now let's say this is our theorem star. Okay, so now let's prove it. Okay, so we can see that, right? So what's the idea to show that? So basically the idea is that, so if we want to show one set is inside in another set. So basically we just show that if we pick arbitrary element in this set, then we show this is also in this set, and then we're done, right? So that's basically the idea, okay? So basically what we do is that we let x is in this set, okay? And of course, you know, we have to assume this is non-empty. This is assumed non-empty. Okay, assume it's a non-empty set, right? So then we want to show this is also in A, right? Okay, and obviously, since we know the average, typical average lemma, right? So we need to construct the gx here, right? And then make it look like, you know, the condition of a vector in this set, right? So can you think what should we do? Right, remember, so the condition of this set look like this or this, right? And for, you know, from this shape or this format, right? So it's very similar to this, right? So the only thing, you know, now we need to connect, you know, this to this, right? The only thing we need to pick is the gx, right? So can you tell me what is gx that here we need to pick? It's sort of given already, right? It's just I, right? The self-information. Okay, so that's basically what we're going to do. Right? Let's see whether it makes sense or not. So basically, we just like gx equals to what log 1 over px. That's it, right? And see whether that makes sense or not. And then we just use the typical average lemma. Okay, and then, so we're going to have the following, right? So now what we're going to do is that we compute this guy, and we bound it by this and that. Okay, so let's see, we just compute this. Right, that's upper bounded by this expectation of log 1 over px and bigger than or equal to 1 minus epsilon expectation log 1 over px. Okay, very good. And then we do some manipulation here, right? So what does that equal to? Right, this should be 1 minus epsilon. Right, and so what is that? Yeah, so that's just entropy, right? And what is that? It's the same, right, times entropy. Okay, And then what we're going to do is that we multiply n on both sides. And let's see what we can get. So in the middle, so what we can get is basically, yeah, we can write everything inside here. So it's nothing but px1, px2 multiply pxn, right? And this is less than or equal to this and that, right? And then from here we can get, so this is nothing but log px bigger than or equal to right? And then obviously, so we can bound px as this. All right. Okay. So now we have an important step here, right? So we can see that, oh, there's a minus sign here. So we can see that for this guy, we can write this as 2 minus n hx and add what? Epsilon times hx, right? And then we let this guy equals to epsilon prime. Okay, and similarly for this one, right? You will do the same for both of them, right? So for and then we can basically get what we want, right? So for this guy, so this is nothing but 2 minus n hx and minus epsilon hx, right? And this guy will equals to epsilon prime. Okay, so that's our condition. So if you remember, so here we need to make this assumption here. Okay, this is the reason. Okay, and now if we see this, so this is exactly now this is exactly the definition of the typical set, right? So together, so this is exactly the definition of our typical set, which is a epsilon prime and x, right? And then we're done. Okay, so now we show that this is kind of bigger. Okay, A is bigger than T. Okay, so in the next class we're going to talk more on the property of the typical set, and then we're done. Okay, great.